Let us get started with this idea of logistic regression. So, in the last module we studied linear regression. So, let us study logistic regression in this module. So, first of all, what is the motivation to logistic regression? There are scenarios requiring qualitative responses. In such cases, linear regression may not be the right choice. So, in the last module we studied linear regression where we had a quantitative response to some prediction variables. This may not be the case for responses that are qualitative in nature. So, let us look into an example. Suppose we are trying to predict the condition of a crop with some diagnosis, and this diagnosis can have qualitative responses such as excessive manure, pest issues, low moisture content, etc., based on a set of predictors x1, x2, so on till xp, right. So, you can think of various scenarios where we may need qualitative responses. Let us form a quantitative response using the following encoding scheme for this crop condition problem. Let this variable y take 3 values 1, 2 and 3, 1 if it is excessive manure, 2 if there are pest issues, 3 if it has low moisture content. One can do a least squares fit to the linear regression model based on the predictors x1, x2, so on till xp. However, one can have a different encoding rule also possible, right. We can have y to take the value 1 if it is a pest issue, to take a value 2 if there is low moisture content, 3 if there is excessive manure in the soil, right. So, what is the purpose of having these different encoding rules? Different encoding rules can give totally different relationships to the conditions. This is very important. Which means we can have fundamentally different models leading to a different set of predictors. This may not be much of an issue if the qualitative response variable has a natural ordering. For example, we go to a restaurant and the food served is in terms of spice gradation, maybe mild spicy, medium spicy and it is hot spicy, then a coding scheme of 1 for mild spice, 2 for medium spice, 3 for hot spice, in that order is reasonable because there is a natural ordering, whereas in the crop prediction problem there was no natural ordering to that response. Now, if we think about binary responses using 0, 1 encoding, there is no problem to this, because if you interpret the quantitative response variable y to be 1 for case A, 0 for case B, then y hat if it is greater than 0.5 we say it is case A, and if it is less than or equal to 0.5 we interpret it to be case B, right. So, therefore, we have a problem here if the qualitative responses are more than 2 variables, I mean the responses are more than 2, we can have ternary or quaternary responses, and for which we need to develop classification methods suited towards these responses. And one such method is the logistic regression. So, this sort of motivates us towards this regression technique itself. Okay. So, let us delve into the details of logistic regression for the binary variable case, and then we can interpret it for binary response to multiple predictors and then for the k class problem. Now, before we begin with the details of the model, let us look into applications where logistic regression can be used. There are many examples. I will state a couple of examples here. The first application would be predicting the failure of a product given various indicators, and these indicators can be various prediction variables. Second would be in the example of a bank loan problem. This is very practical. If you were to predict if a homeowner defaults on a loan given a bank balance history, I think this would be a useful tool for issuing the loan itself, right. So, or predicting the health of that individual who is owning that home. Now, these are examples of situations where logistic regression can be useful. Let us get started with a simple linear regression case. P of x is alpha naught plus alpha 1 x, where x is the prediction variable, right. We start with a simple linear regression case. Now, observe, depending on the value of x and these coefficients alpha naught and alpha 1, one can have p of x to be less than 0 or p of x to be greater than 1. This is not so much of an issue unless we would like to interpret p of x in terms of a probability, right, that we would like to interpret p of x in terms of a probability condition on the data x or the predictor here, and we need to limit p of x between 0 and 1, because it has to be a valid function, right, a probability function. Now, p is a function going from R to a value between 0 and 1, and one such function that satisfies this constraint for us is the logistic function. So, let me get into the details of how the logistic function is written. So, the logistic function is given by the ratio of two terms here. The first term is e power alpha naught plus alpha 1 x in the numerator, and in the denominator it is 1 plus e power alpha naught plus alpha 1 x. And you can interpret in terms of odds, right. For example, p of x, if it is a head, 1 minus p of x corresponds to a tail. So, you can interpret this in terms of odds, and p of x upon 1 minus p of x takes this value e power alpha naught plus alpha 1 x, and this ratio can take the values between 0 and infinity, because p of x is between 0 and 1. So, this can take the values between 0 and infinity. Now, taking the logarithm, log of p of x upon 1 minus p of x, this can be written as alpha naught plus alpha 1 x. Now, this is a linear function, because 1 unit increase in x can have alpha 1 units increase in the logarithm of these odds, and we interpret these log odds as the logarithm of the likelihood function, right. There are a few points to note. First, there is no linear relationship between p of x and x, and the rate of change in p of x per unit change in x depends on the current value of x, right. So, with this setup of the model, our next step is to estimate the regression coefficients, which are alpha naught and alpha 1. Now, let us see how we can get to this problem. We shall shift gears on our metric. In the linear regression case, we considered the residual square sum as our metric, and this was leading to a quadratic cost that we set up to optimize. But here we will look into the maximum likelihood function, and it has more better, it has better statistical properties. Okay. So, let us formulate the likelihood function. Capital L stands for this likelihood function. L of alpha naught alpha 1 is the product of all p xi's where yi equal to 1 times product of all yj 1 minus p of xj where yj takes a value 0. So, this can be compactly written in this form, right. So, I can take yi can take 0 or 1, and the probability will be corresponding to that observation I, which is given by p of xi, and yi sort of is indicating here that it is 0 or 1. Now, this quantity L of alpha naught comma alpha 1 has to be maximized over the variables alpha 0 and alpha 1, because those are our unknowns, and we have to maximize with respect to these unknowns to get a better fit to the model, that is we want the parameters to fit the model. So, put in compact terms, we need to choose alpha naught alpha 1, the estimates of alpha naught and alpha 1 that are optimal. The star indicates optimality and the hat indicates it is an estimation that maximizes this likelihood function. Now, if you look into the likelihood function itself, it looks rather messy because we have a product of all these terms, and directly it is difficult for us to optimize this quantity. We use a familiar trick. We take logarithms. The advantage of taking logarithm is log is a monotonic function. Since log is a monotonic function, we can take the logarithm of the likelihood function, it does not change its properties. So, let us call small l of alpha naught comma alpha 1 as a logarithm. We define this to be the logarithm of the likelihood function. Now, we simplify the equation that we had earlier, that is our likelihood function in terms of this log likelihood, and we do the math, we get this form here, right. This is the form that we get. So, all we do is when you take the log, it translates into a sum. So, it is summation I equals 1 to n y sub I log p of xi plus 1 minus y sub I log 1 minus p of xi. So, this seems to be tractable, but let us slightly rearrange this equation, because we want the variable yi to be sticking out in one of the terms and left aside for the other term. So, this simplifies as sigma I equals 1 to n log 1 minus p of xi plus summation I equals 1 to n yi times log p of xi upon 1 minus p of xi. Pretty straightforward simplification. Now, you can interpret this second term. So, this is first term and this is second term. So, given p of x upon 1 minus p of x as the odds. This is basically the log of the odds, and we can get a linear relationship here, right, from our previous discussion, and we will use that property towards our simplification. Now, we get this quantity to be minus summation I equals 1 to n log of 1 plus e power alpha naught plus alpha 1 x I plus summation I equals 1 to n y sub I alpha naught plus alpha 1 x I. This is just from the linear term in the logistic regression model, right. When you take the log of the odds, you get a linear term, and that is what it is. Now, once we have a sort of easy looking equation, we can take the partial derivatives with respect to the variables alpha naught and alpha 1, set that equal to 0, and verify that indeed these quantities are maximizing by taking the second derivative and checking this to be less than 0 for maximum condition, right. This is what we will do. Now, it is straightforward calculus. We take the partial derivatives and we set this equal to 0, right. Day by L upon day by alpha naught, this translates to this equation. So, the first term, so this is a logarithm of a function. So, you take the derivative with respect to alpha naught. So, you have 1 upon 1 plus e power alpha naught plus alpha 1 x I, and you have to take the derivative of this function, which is e power alpha naught plus alpha 1 x I, and the coefficient sticking before alpha naught is 1. So, therefore, it simplifies to this quantity here, and the second term is, if you take the partial derivative with respect to alpha naught, it just results in sigma I equals 1 to n y I, and that is what we have here. Similarly, we do the same sort of math, taking the partial derivative of the log likelihood function with respect to the parameter alpha 1. We have 1 plus e power alpha naught plus alpha 1 x I in the denominator, because we have a log function, and taking the derivative of the argument within the log, we have e power alpha naught plus alpha 1 x I, and if you take the derivative of alpha 1 x I using this chain rule, we get x I. So, this is correct, and then we have summation I equals 1 to n y I x I, because that is a partial derivative with respect to alpha 1. So, we have all these 4 terms now, but what is important is to see if we can solve equations C and D in closed form. Unlike the linear regression case, where we were able to solve for the parameters alpha naught and alpha 1 with some manipulations, this is not easy to solve. So, solution to equations C and D is not trivial, because they are transcendental equations. So, one involves e power something and other is a normal summation like this. To solve for alpha naught and alpha 1, we have to use numerical techniques, and this is not the subject of this discussion. So, once you set up the partial derivatives, you can use an appropriate solver to solve for these variables. And once we get the optimal estimates, our goal would be to predict the responses. So, p hat of x is given by this quantity e power alpha naught hat star plus alpha 1 star hat x plus 1 plus this quantity here. That is, you plug in x, you compute alpha naught star hat and alpha 1 star hat, The hat stands for an estimate, the star stands for the optimal condition. Okay. So, once you plug in x given the optimal estimates that you have, you can predict the qualitative decision by interpreting this in terms of a probability. For example, given the bank balance condition, you can figure out if the defaulting condition is a yes or a no over a home loan. Okay. Now, we have formulated a simple model for a single variable towards binary logistic regression. A natural way is to extend the binary response given p predictors. So, let us see how we can do this. But before we delve into the details, there are some important applications where we have to think about the usage of this model, right. Let me give you some examples, motivating examples. Imagine I am an undergraduate student. I have to decide if I have to go to pure science or engineering, and what I have as inputs with me are my grades and my likes and dislikes, right. Given these variables, I want to decide if I want to join pure science or engineering. The second could be, for example, in an election situation, imagine that there are two parties where an individual can vote, and given the demographic characteristics and likes and dislikes, what can I say whether I would vote for party A or party B. You can also think about this as an election result if party A wins or B wins depending upon exit poll and other conditions, right. There are many such situations that we encounter where we may require logistic regression. Now, let us see how we can formulate this model. Okay. So, from our ideas discussed earlier, right, we said the log of p of x upon 1 minus p of x was a linear function which is alpha naught plus alpha 1 x. So, this idea can now be extended for x1 through xp being the prediction variables, and we say that log p of x upon 1 minus p of x is alpha naught plus alpha 1 x1 plus dot 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 till alpha p xp. So, I repeat again, alpha 1, alpha 2, alpha 3, alpha p, I mean including alpha naught, these are all the unknowns that we need to estimate, and alpha, I mean x1, x2 so on till xp, they are the predictors. Now, straightforward algebraic manipulation will give us this equation for p of x. It is a ratio of two terms, e power alpha naught plus alpha 1 x1 plus dot 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 alpha p xp upon 1 plus exponential alpha naught plus alpha 1 x1 plus dot 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 plus alpha p xp, right. This is what we have. Now, setting up the likelihood function. So, again we have indication on this variable yi being 0 or 1, but we have to look at this function p of x1 I so on till xpi, right. These are prediction variables for the observation I, and yi is this binary response which can take 0 or 1. So, we have sort of like two variables here, right. I is the observation and yi is the response, and 1 through p are these prediction variables. So, we formulate the likelihood equation straightforwardly from how we did the binary case, that is just with one variable, one predictor. Our goal would be to choose these parameters alpha naught through alpha p that maximizes this likelihood equation. Sort of very straightforward, like how we did the binary case. If you got the intuition there, it should be straightforward for you to solve this problem. So, what you could do, you could simplify this problem, you could assume some assumptions, you can make some assumptions to interpret this quantity here, which may not be straightforward for us to simplify. And if we make certain assumptions to break this joint probability term, then we can kind of simplify this equation towards doing an ML estimate over the parameters. Okay. Now, our goal does not stop here, we can sort of generalize it to the K class problem. Now, consider the linear predictor with p predictors and observation I leads us to an outcome K, right. I can have K classes, small k can go from 1 to capital K, right. It is a K class problem. So, I make an observation, does it belong to these classes. Now, let us see how we can generalize this approach to this K class problem. So, first we formulate the linear predictor, and this linear predictor I call it phi of k comma I, which is given by this equation here, alpha 0 comma k plus alpha 1 comma k times x 1 comma I plus dot 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 plus alpha p comma k x p comma I. So, what does this mean, right? What does this mean? So, these x 1 I, x 2 I, so on till x p I are prediction variables, right. So, the first index stands for the prediction variable. So, 1, 2, 3 dot 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 till p, they indicate the prediction variables for the observation I, and the unknowns which are these alpha j comma k, where so in alpha j comma k, j can go from 0 to p, they are basically our regression coefficients, which is what I mentioned here, and k indicates the outcome, right. So, there are 3 variables playing a role here. So, one is this prediction variable, and these are regression coefficients, and I is our observation. At a first glance, this looks quite complicated, because we have p plus 1 terms here, right, and this can simplify dramatically if we can use a vector notation and write this compactly. Now, phi of k comma I can be interpreted as the dot product between two vectors alpha k and xi given in this form. So, alpha k is basically a stack of all the regression coefficients, right, corresponding to the p predictors and also for the 0 case for the outcome k, right, and xi is basically a stack of all the p predictors x1 through xp for observation I, and the first coordinate is basically 1, consistent with the way we have defined the linear predictor. Now this is compact. Now we would like to interpret this K class classification problem in terms of independent binary regressions. For the binary regression it was very easy because we could take the odds. There were only two cases, 0 with respect to 1 or 1 with respect to 0, and we could simplify the problem. But for a K class problem we cannot take the odds like this, but the idea is pretty straightforward. What we do is we fix one of the outcomes to be a pivot, and then with respect to the pivot we look into the k minus 1 other possibilities, and then we regress with respect to the pivot. So let us see how we can formulate this. Okay. Now log, taking the natural log, I have p of yi equal to 1. So this is a very important note here that I have written here for notational use. That is, I have the outcome to be 1 through k, right. The pi for the ith observation, the variable yi can take 1, 2, 3 so on till capital K, and this must be interpreted as the probability that this outcome is 1 conditioned to xi, which is basically this vector comprising of the predictors for 1 through p, right, and this is how we have to interpret. So instead of giving this conditioning with respect to xi, I just omit this conditioning for notational use and interpret it as p of yi equal to 1, because otherwise I have to give this conditioning everywhere throughout. So keeping this notation, you have to follow the mathematics as appropriate. Now the log of this sort of likelihood, keeping the outcome k as a pivot. So this is our pivot. We get this as alpha 1 transpose xi, and doing this for all the cases we have log of probability of yi equal to k minus 1 divided probability yi equal to k is alpha k minus 1 transpose times xi. So we have all these terms that are listed here. Now let us simplify this slightly further. So the probability, that is, I can predict that the outcome is 1 is equal to the outcome which is k scaled by this exponential term, right. This is straightforward, just you take the exponentiation on both sides of this equation and you just simplify it, you get it is straightforward, right. You take the exponential here, p of yi equal to 1 is basically p of yi equal to k times exponential of alpha 1 transpose xi, okay. This is straightforward, and you do this for all the k minus 1 possibilities, you get the set of equations. So you have this pivot sticking here, which is probability that the outcome is k scaled by this exponential term that depends upon these regression vectors alpha 1 to alpha k minus 1 and the variable xi that depends on the observation I. Now the sum of all possible outcomes should be 1. This is our probability sum result. So the probability that the outcome is k is 1 minus the summation of all the outcomes from 1 to k minus 1, and doing the straightforward math we land up with this equation, probability p of yi equal to the outcome capital K is given by this quantity 1 upon 1 plus summation j equals 1 to k minus 1, capital K minus 1, e power alpha j transposed xi. Okay. Now, P of yi equal to j, for the jth outcome we can just compute it straightforwardly, because we know that this quantity 1 upon 1 plus the summation k equals 1 to capital K minus 1 exponential of this term, that is the probability that the outcome is equal to capital K, and you have this exponential modulation term here. So, therefore, we can interpret this quantity as the probability that our outcome is j for the observation I. So, you have to be very savvy about it. The observation is I. For every such observation you have p predictors, and that is the key here. Now, the goal would be towards estimating these regression vectors alpha k, small k equals 1 to capital K, and using maximum a posteriori probability criterion we can compute this. So, the details of this derivation you can refer to any statistical modeling book for more details for the derivation for this multi-class problem, but for the interest of this class we will stop here, because this is where our regression ends. If we are going through a pattern recognition class, then this may be a few lectures to continue with. Okay. So, we will stop here, but you have hopefully gotten a feel for regression techniques, right, both the linear and logistic regression, and this can be useful for classification problems based upon supervised learning. Okay. So, we will stop here and we will continue with our discussions for the next module.